Yeah, so we're going to switch gears back to a bit of physical geography, but I did like that story map idea. I saw my first conference presentation delivered via story map the other day, and I thought it was really cool. But today, the research I'm going to talk about is a small part of a larger project that's associated with the Trent Aquatic Research Program. And before I begin, I'd just like to acknowledge the principal investigators in the Department of Biology listed at the bottom of the slide there. So spatial heterogeneity within lakes. Often we tend to think of lakes as singular units, and we often treat them that way when we sample them in broad scale environmental monitoring programs. But as you can see on this map on the right, lakes can be spatially heterogeneous. They can vary in their morphologies, vary in their bathymetries, water movements, and the substrate within their shorelines. Surrounding a lake, there can also be spatial heterogeneity in the stream water inflows, shoreline development, and the land use and land cover composition of their watersheds. Finally, lakes can be heterogeneous vertically. So if you've ever gone swimming in a lake and you felt that warm layer of water at the top, that cold layer of water by your feet, you've experienced thermal stratification, whereby there are vertical differences in the water due to a lack of mixing. And these spatial heterogeneities can in turn affect the water chemistry of lakes, the growth of phytoplankton, zooplankton, and even the movement and behavior of fish. But despite all this heterogeneity, when we go out to sample lakes, we still often just sample at one location and use that sample to infer its ecosystem health. So through hypothesis-driven research and long-term environmental monitoring, the Trent Aquatic Research Program aims to address threats to the ecosystem health of the Kawarthas lakes and to better understand the relationship between aquatic organisms and their environment. But to do that, to achieve these objectives, we also need to understand the effects of within lake heterogeneity, especially within these larger lakes in the Kawarthas. So to do that, we set our sights on Stoney Lake. Regionally, Stoney Lake is an important lake. It's part of the Trent-Severn Waterway. It has significant cottage and recreational use, and it's of importance to local First Nation communities. Stoney Lake is also an interesting lake geographically. You can see on the map on the right, maybe not with this, I have a laser pointer in my pocket. On the map on the right that it's, I can't see it at all, that it's divided into three basins. We have Upper Stoney here at the top, Lower Stoney in the middle, and Clear Lake at the bottom, with Clear Lake containing the primary outflow of this system. If we look on the map on the left, we can see that the Stoney Lake watershed is actually quite large. And in fact, it spans two physiographically distinct regions in Ontario, the Canadian Shield to the north and the Great Lakes St. Lawrence lowlands to the south. If we kind of focus in on the Upper Stoney Lake subwatershed right here, you can see that it's much smaller, and in comparison to the rest of the Stoney Lake watershed, it primarily drains the Canadian Shield. The Stoney Lake subwatershed, or the Upper Stoney Lake subwatershed, also differs from the subwatersheds of Lower Stoney and Clear Lake in its land cover composition, where it drains a much more natural landscape with more forested cover. And these differences in watershed physiography and land cover are reflected in each of the basin's water chemistries, with Lower Stoney and Clear Lake having about twice the amount of nutrients compared to Upper Stoney. So to better understand this within lake heterogeneity in Stoney Lake, we went out and sampled 22 locations across the lake this past summer. We targeted these locations to the deeper sections of the lake and ensure that there was representative sampling in each of the three basins here. And at each of these locations, we took vertical measurements of various limnological variables. And to do this, we used a vertical profiler. A vertical profiler is a sensor-based instrument that can measure numerous limnological variables, including chlorophyll, dissolved oxygen, temperature, conductivity, and many more at a vertical resolution of less than 5 centimeters. So what this means is we have a measurement of each of these variables every 5 centimeters as you go from the surface of the lake all the way to the bottom of the lake. And just for the sake of time, I'll show you the results for chlorophyll, dissolved oxygen, and, chlorophyll, which is a measure of the total algal biomass in the lake, dissolved oxygen, which is what heterotrophs like fish use to breathe, and color dissolved organic matter, which are the organic molecules leached from decaying materials like detritus and leaf litter that make water look brown in color. But before I do that, I'll just go through the GIS ArcPro methods that I use to map out these data. So first, we had too much data. So the first step that I took is I took all the vertical profiles and aggregated them to a coarser vertical resolution of 1 measurement per every 30 centimeters. Next, I associated each vertical profile with its spatial location and combined them all into one Excel file with a long format and an XYZ coordinate system. This Excel file was then imported into ArcGIS Pro and converted to a 3D point shape file. I then used Empirical Bayesian Kriging 3D to generate a 3D geostatistical layer of each limnological variable across Stoney Lake. These geostatistical layers could be explored in 3 dimensions in ArcScene, but I prefer working in the raster format, so I used a Python script to export individual 2D raster layers of each limnological variable at a 1 meter interval from the top to the bottom of the lake. And this is what the results look like for chlorophyll-a, so the amount of algae. Visually, we can see that there is more or higher chlorophyll concentrations at the surface of the lake than at the bottom of the lake. And this makes sense because as you go from the top to the bottom of the lake, light availability also decreases. It gets darker at the bottom of the lake. Algae, algae and phytoplankton, need this light for photosynthesis, so we'd expect that there would be lower concentrations towards the bottom of the lake. If we just look at the surface of the lake, we can see some spatial heterogeneity here. In particular, we see lower chlorophyll concentrations in Upper Stoney, kind of mixed chlorophyll concentrations in Lower Stoney, and higher chlorophyll concentrations in Clear Lake. And these spatial differences likely reflect those differences in water chemistry that I mentioned earlier, with those greater nutrient concentrations in Lower Stoney and Clear Lake, acting like a fertilizer to support increased algal growth. Here are the results for colored dissolved organic matter. It's a little bit hard to see on this animation due to the wide range of values that we observe in Stoney Lake, but there is greater concentrations of dissolved organic matter in Upper Stoney compared to the rest of the lake. If we kind of pause this animation at a couple still images here, we can better see that there is indeed higher concentrations of CDOM in Upper Stoney, which seem to become more evident the deeper you get in the water column. And this, like chlorophyll, likely reflects those differences in watershed physiography. If we remember, Upper Stoney drains a much more naturalized catchment, and this watershed actually has fewer lakes along its river network. So there's a greater opportunity for this organic matter to leach into the water and stick around here. Lastly, we have dissolved oxygen. And you'll notice here that at the surface of the water, there's a uniform dissolved oxygen concentration. And as you get lower in the water column, we start to see some of that spatial heterogeneity. Oxygen dissolves into the water at its surface through gas exchange, which is driven by wind, waves, and water turbulence. So this uniform dissolved oxygen concentration at the surface actually makes sense. But as we get deeper into the water column, thermal stratification prevents that water at the surface of the lake from mixing with the water at the bottom of the lake. The heterotrophic organisms living at the bottom of the lake, specifically microbes that live in the sediments, consume all this dissolved oxygen and decrease its concentrations at the bottom of the lake. If we go around the lake, we can see that there are some pockets of low dissolved oxygen in Lower Stoney, but for the most part, Lower Stoney is too shallow for thermal stratification to occur. So the entire water column is connected with the atmosphere. If we go to the deeper Clear Lake, we can see that at the bottom here, there's nearly zero dissolved oxygen. And when we move to Upper Stoney, even though it is thermally stratified here and much deeper than 9 meters, that we see sufficient dissolved oxygen throughout the entire water column. So in conclusion, we observed significant spatial heterogeneity in the 3D distribution of limnological variables in Stoney Lake. And this raises some further questions related to temporal variation, variation in the biogeochemical processes that control these limnological variables, and variation in the movement and behavior of fish. This last question is going to be addressed in the next phase of this project. Currently, there's an array of underwater acoustic telemetry stations throughout Stoney Lake, and there's about 60 fish that have been tagged. These fish movement data will be combined with this water quality data to better understand how fish use the lake and better understand how threats like changing water quality and dissolved oxygen depletion will influence these organisms. So if you have any interest or further questions, I encourage you to check out some of these websites, and you can always send me an email. And Graham, one of the principal investigators here, just walked in. So if you have any fish questions,